Good morning, respected professors and the participants. I am Anindita Bhattacharjee. Today I am giving presentation on the topic Design of a Compact UWB MIMO-Diversity Antenna for Wireless Communication Applications. Now the introduction part. MIMO. MIMO is specially an acronym. It stands for Multiple Input, Multiple Outputs. In this system, multiple antenna connected in the transmitting side as well as in the receiving sides. This MIMO system significantly improves the system channel capacity, overall quality of the communication system in the UWB band. There are different types of MIMO configurations available. Here, a 2 by 2 MIMO antennas given. In this figure, two antennas are connected in the transmitting side to transmit the signal from the base station, and two antennas are connected in the receiving side to receive the signals. But during designing a MIMO system, one main problem is the mutual coupling problem, because in MIMO system, antennas are closely packed. That's why there is a possibility to occur the mutual coupling problem, and this mutual coupling problem deteriorates the performance of the system. Now the fractal. In my design, I used fractal structure. Fractal is a branch of the mathematics. It always deals with the irregular shift patterns, and the word fractal was first used by mathematician Benoit Mandelbrot, and this fractal structure successfully modeled different complex natural objects like seashore, thunderstorm, etc. Now the UWB. That UWB means ultra wideband. In the year of 2002, FCC assigned an unlicensed band from 3.1 to 10 GHz as UWB band. This UWB band require less amount of power if we compare with 2G mobile phones and 3G mobile phones. And this is a wireless technology. It's used for transmitting digital data at very high speeds with less power, and it is very much suitable for different short range high speed data transmission. Now evolution of the antenna design. This is the top view and bottom view of my antenna structure. Roser R4350B with dielectric constant 3.5 and loss tangent of 0.004 is used as the substrate material for my proposed design. The thickness of the substrate is 1.6 mm, and the overall dimension of the antenna is 18 by 26 mm square. It is very much compact. In the top view, two radiators are placed, two identical radiator, and tapestry feeding structure is used to apply feeding. Post fractal structure used in the radiators to achieve the ultra wide bandwidth. In the bottom side, the ground plane associated with the isolation structure and notching structure is there. This is the notching structure. In this structure, two stub slanted at 45-degree connected with a T-shaped stub, and there one notching slot is used to achieve the notching. This notching because in the UWB range different bands are there. To avoid the interference from this band, I designed a notching structure, and it provides notching in the WLN band. Okay. Now the isolation structure. In this isolation structure, I used Minkowski fractal structure up to second iteration. By using this fractal structure, the mutual coupling problem of the proposed antenna is reduced without increasing the overall dimension of the antenna. These are the parameters with dimensions used in my proposed design. Now the ground plane. The ground plane placed on the opposite plane of the substrate, and it acts a very much significant role on the performance of the designed antenna. This ground plane not only improves the impedance matching, but it also upgrades the isolation among the radiating elements. First, a rectangular shaped ground structure is introduced. After that, Minkowski fractal structure up to second iteration is implemented. Okay. Now, this is the S21 plot for the proposed antenna. From this plot, we can see that with every iteration, the isolation property is improved, and the antenna provide better isolation less than minus 16 dB up to 6 GHz and minus 18 dB for the rest of the band. Now, to know the effectiveness of the decoupling structure, the surface current distribution pattern is given. In the first case, when a simple rectangular shaped ground plane is used and Minkowski structure is not present and port 1 is excited and port 2 is connected to the load, the maximum amount of current flows on the ground plane and it creates mutual coupling problem. Now, to reduce this mutual coupling problem, Minkowski fractal structure is used, and we can see from this figure 2, 3 and 4 that very less amount of current flows on the ground plane, and from this figure we can see that maximum amount of current concentrate on the second iteration Minkowski fractal structures. This fractal structure, without increasing the overall dimension of the antenna, improves the isolation properties of the antenna. Now, S parameter. According to IEEE, the portion of the curve S11 curve lies below minus 10 dB line is represented as the bandwidth of the antenna. Here, the proposed antenna provide ultra wide band and it provide bandwidth from 3.1 to 20 GHz, and it also provide band notching at the 5.5 GHz. The band notching is at the WLN band. This is the fabricated figure of the proposed antenna. Now, the gain and efficiency plot of the antenna. The gain and efficiency, both this plot drop at the 5.5 GHz. The 5.5 GHz is the resonant frequency of the band notching structure, and the efficiency curve which drops at 5.5 GHz, it indicates that antenna is appropriate to work in the high interference surroundings. The gain of the antenna ranges from 0 to 7 dB, and but at the notch band it drops to minus 4.5 dB. Now, the copole and crosspole radiation patterns. The antenna provide almost omnidirectional radiation pattern over the entire frequency range, but at the high frequency range the patterns deteriorated because of the radiation loads. Now, ECC and diversity gain. ECC and diversity gain both are very important parameter to examine the performance of any MIMO antenna system. ECC represent how much amount of correlation presence in the antenna element. This plot curve shows the ECC curve for the measured and the simulated. The ECC parameter ideal value is 0, but in practical acceptable value is less than 0.5, and it is came from the proposed structure. The diversity gain evaluated value is the greater than 9.95 dB, and this is the simulated diversity gain plot. Now, these are the references from which I get some ideas. Thank you.